So actually we need to do the Fourier transform of this function. Yeah. So which is actually Fourier transform of phi k. So yeah. So it will look like so maybe we can just skip this part because it's just a normalized factor. We don't really need to care about it, and actually we don't we have not really normalized it yet. So maybe we can just try to yeah, maybe we can write it like this. So it's like the integration of this part. Actually, this part is k minus k0, or maybe first we can just ignore this part, and then maybe we can also make sigma. Maybe we can just keep sigma. Maybe we can just calculate these parts, which is fine. So we multiply it by minus j kx dk. So it's just like this is actually phi, or this one should be phi k minus k0, k plus k0. So you know that the Fourier transform will be like this part multiplied by exponential j x k0, something like that, or plus or minus, I don't really remember. Should be multiplied by this term. So it doesn't really matter because this is if you take the absolute value, it will be 1. So this is a bit complicated function, but actually it's not so difficult to calculate. So we can just use exp, which is nothing but e to a power, but actually we can just write the other stuff down. So for this part, we can write it as k over square root of 2 sigma k, this term to be square. And then we have minus jkx. So we will have jx, and then we also have k. So we try to make it like this, square root of 2 sigma k, and then multiply it by square root of 2 sigma k. So they cancel each other, and we also multiply it by 2 and then divide it by 2. So this is the b, this is b squared, this is b, this is a, somehow like that. So we can just plus, not plus, minus, should be minus j x over square root of 2 sigma k square plus jx sigma k over square root of 2 square. So this is minus b square minus 2ab minus a square, and then we plus this term because already don't have this term. So we will actually have decay. So we will actually have this term to be a constant independent of k. So it is just a term like exponential to this term j square is minus 1, so it will be minus x squared sigma k squared over 2. And then the other one will be like this. Exponential 2 minus k plus k over square root of 2 sigma k plus this term, jx sigma k square, something like this, dk. Okay. Okay, so we have still some space. So actually we can just substitute this stuff. We can try to make u equals to or it should be like this, should be like, it should be like minus this square, because we have minus here, so it should be minus this term to be squared. So actually now we can just let u equals to k over square root of 2 this term plus jx sigma k over square root of 2. So we can have a du equals to dk over square root of 2 sigma k. So we can just make some simple substitution. So next we can just substitute it here, and then it will becomes dk. So it will becomes sigma square root of 2 sigma k exponential to this term and then look like this, or we can actually write it as exponential to minus u squared du, something like this. So in the front we have some constant, and then we still have this one. Have you learned it in a calculus class how to calculate this integration?
They just told us that
This is the square root of 2 pi. Square root of 2 pi. Actually, it can be calculated like this. We can just make maybe, suppose we have I equals to this one exponential to minus x squared dx. So I squared will be nothing but exponential to minus x squared dx, and then exponential to minus y squared dy, because this one and this one is actually the same. We only have x and y, but after doing this definite integral, it will just remove it. So actually we can make some variable substitution. So variable of substitution. So we can make r equals to square root of x squared plus y squared. And actually just change the Cartesian coordinate to polar coordinate. And then theta will be arctangent of y over x. So this stuff will be exponential to minus x squared, exponential to minus y squared. So I square will be like exponential to minus r squared. And then this dx dy change it to not this one, should be so dx dy will be like r dr d theta, r dr d theta. So we will have dr dr d theta. And actually this is the polar coordinate. So this is from 0 to infinity. And the theta is from 0 to 2 pi. So this integration is easy to calculate because r dr is 1/2 dr squared. So that this one is easy to calculate, and then it becomes 1 because this is 0, this is infinity, so it's substituted. If it is 0, substitute it is 1, and then the other term is 0. So I squared will be like square root of 2 pi, and then we find that I is nothing but square root of 2 pi. Square root of 2 pi. So this is nothing but square root of 2 pi. Square root of 2 pi, which is a constant. So this is the interesting point for the Gaussian. This is called the Gaussian integral. The Gaussian integral. And if it is not integrate from 0 to infinity or minus infinity to infinity, then there are no numerical solution. For example, if you integrate from 1 to infinity, or maybe from 0 to 1, then you need to check it on some table or use the computer to calculate this integral. Only you integrate from minus infinity to infinity or 0 to infinity, then you can come up with a closed solution like square root of 2 pi. And you know that now this is the function of x, and this term is actually the function of x. So it will look like this is square root of 2, this is square root of 2, so it's 2 square root of pi sigma k exponential to minus sigma k square 2 x squared. We just reverse the order. Okay, so next part is originally we have phi k equals to or proportional to exponential to minus k squared over 2 sigma k squared. And then we know that phi x is proportional to exponential to minus sigma k squared and over 2, and then x squared, something like that. So which means that this one is the standard deviation. This one is the standard deviation. And this one is the standard deviation is like exponential to minus x squared 2 over sigma k squared. Something like this. So for this one, the standard deviation is sigma k. For this one, the standard deviation is 1 over sigma k, which means that this one becomes larger, this one becomes smaller. So it will feel like in the k domain, if this normal distribution is wider, and in that case, in the x domain, this one is narrower, and vice versa, So which means that this one is wider, this one is narrower, which means that this one has more uncertainty, this one has less uncertainty, and vice versa. So, but in that case, sigma x, sigma p should be larger than 1/2 of h bar. So actually, we know that the probability of k should be this one. Should be this one. Should be this one. So it is still like exponential to k square sigma k. So you can regard it as 2 times 2. So actually, the sigma k, maybe we can call it k bar here, k prime here. So which is actually sigma k prime over square root of 2. And for this case, pxx is and it is proportional to this stuff, which is exponential to minus x squared like this, sigma k prime. And then you can put 2 here and then 2 here. So sigma x should be 1 over square root of 2 sigma k prime. And we finally know that sigma x, sigma k should be 1 over 2. So this is not that one. This is sigma p. This is sigma p. But actually we know that we have this one. P equals h bar k. Which means that we have a p equals, P equals h bar k, which means that sigma p equals to h bar k, sigma k. P equals sigma h bar k. So in that case, well, this sigma k. Or maybe there's some. So P equals sigma k. Oh yes. Yeah. So actually we have this one, we have this one. So we can just multiply by or maybe we have a larger or equal to. So we can multiply both sides by h bar sigma k larger or equal to 1/2 of h bar. So this one is sigma p. So we have sigma x, sigma p larger than square root of h bar over 2. And for Gaussian distribution, it satisfies the equal sign. It doesn't really he doesn't really prove why it is always larger, but actually no one, not any experiment can have ever violate this uncertainty principle. Okay, so we have a sample problem. So here, assume an electron is moving along x-axis, and that you measure its speed to be like this, which can be known as a precision of 0.5%. What is the minimum uncertainty? The minimum uncertainty is allowed by the uncertainty principle in quantum theory, with which you can simultaneously measure the position of the electron along the x-axis. So you just substitute it into the Heisenberg uncertainty principle, and that's it. So here we have the speed and the precision, which means that yeah. So px is mvx. So the momentum is mv. P equals mv. So which is a electron. So the mass is 9.11 times 10 to minus 31, and then the speed is 2.05 times 10 to the 6th power. So which is 1.87 times 10 to minus 24 kg meter per second. And actually delta px is 0.5%, which is 0.005 px, which is 0.005 times 1.87 times 10 to minus 24, which is 9.35 times 10 to minus 27 kg meter per second, like this. So we will have delta x. Maybe we can just follow the textbook, which is delta x delta p, which is larger or equal to h bar. Maybe we just follow that. So it is like x. Delta x should be larger or equal to h bar over delta px. So this is 6.63 times 10 to minus 34 over 2 pi, and this one is 9.35 times 10 to minus 27. So it turns out to be 11 nanometer. 11 nanometer. So when you just read the book, the Heisenberg uncertainty principle is nothing but delta x delta p. X is larger or equal to h bar, but actually it's related to the Fourier transform. So any problem, any question regarding to this one? So if no, we'll talk about the refraction from a potential step. So we send a beam of a great many non-relativistic electrons， 就是没有考虑相对论效应，然后我们考虑很多的电子So each of total energy E along an x-axis through a narrow tube， 就是一个很细的管，So initially they are in region 1. They are in region 1 where their potential energy is U equals 0. So this left side is region 1. This is region 1. And the potential is 0. You can feel like there are no, maybe this is the reference voltage. This is the voltage there defined to be 0. The voltage there defined to be 0. So for this part, it is region 1. And then, but at x equals to 0, they encounter a region with a negative electric potential. So this part is VB. This part is VB, which is smaller than 0. And as long as this one is an electron, electron, which means it has a negative charge. It has a negative charge. So as long as this VB is smaller than 0, this voltage will put this electron back. This electron cannot go to this part because this is a lower voltage. It is a negative charge. So the step is said to have a height UB, which is the potential energy. An electron will have once it passed through the boundary at x equals to 0. 所以我们如果用古典物理的角度去看的话，那这个电子啊，一定要比右面这个potential 它的 kinetic energy 啊，要比这个 potential energy 来得高，它才能够爬过去。就好像说前面有一个台阶，我一定要脚抬得比它高，我才能够过去。或者是说前面有一个高的一个阶梯啊，我手上拿一颗球，我那个球啊一定要有一个比较大的动能才能够丢到上面去，啊，这是这个意思。但是量子力学的话是不一样的，啊，它是不一样的。它这个的话是说，就算这个电子有一个比较高的 kinetic energy 啊，它也有几率反弹回来的。So classically, the electron has too much energy to be reflected by the potential step. 所以它就是说，古典物理的话，只要这个电子如果动能太低的话，它就会撞墙，就是反弹回来嘛。那如果你动能够高的话，它就会穿过去，它就好像没看到这个一样啊，只要比它高。However, for the quantum world, it's not that case. So actually, we need to solve the Schrödinger's equation. So this is the Schrödinger's equation. This is the Schrödinger's equation. You have learned maybe a few pages ago. So in region 1, U is 0. U is 0. So this one reduced to d squared phi dx squared plus 2me over h bar square phi equals 0. So this one is pretty easy. It's just a constant coefficient second ODE. So although there are many variables, so you can just regard this k to be square root of 2me and then over h bar. So you can just regard k is like this, and then the original equation will look like second derivative of phi dx squared plus k phi equals to 0, like this. So actually you can have s squared plus k equals to 0, or k squared. This one should be squared because we already have the square root there. So it's like this. So s to be plus or minus jk or ik. So we have the solution like this. We have the solution like this. So at region 1, the solution will look like that. And for region 2, this UV is higher because you can consider this UV will be E times VB. So maybe you can take E to be a negative value, and also this VB is also negative. So UB is positive. This is negative because it's an electron. So this is a positive value. And here, for region 2, this is region 2. This is this is region 1. This is region 1. So for the right hand side part, U is UB rather than 0. So here we can just make, so that equation will look like this, and then plus 2m, and then E minus UB over h bar square, and then phi equals 0. So we know that E is larger than UB. E is larger than UB because this is kinetic energy. Kinetic energy is larger than UB. We already assume that. So this whole term is still larger than 0. It's still larger than 0. So for this part, we can assume KB equals to this term. KB equals to this term. So this will reduce to d squared phi dx squared plus kb squared phi equals 0. So actually it's low similar. The only difference is k, you change k to kb, but with different coefficients. And now assume that the electron will go in the x direction, because for region 1, this electron will go to this, will go from here to here. Maybe it will reflect, so it may go back. So this is go in the positive x-axis. This goes in the negative x-axis. But after this electron go through, it will only go in the right side. It will not go back because the right side doesn't change. So in that case, we will assume that d equals to 0. So the only remaining term is the first term. Is the first term. And in that case, the wave function should be continuous. Phi should be continuous, and so as the phi prime should also be continuous, which means that phi 10 should be equals to phi 20, and then you substitute the value, which means it will be become a plus b equals to c. A plus b equals to c, and also phi prime is continuous. Phi prime is continuous, so phi 1 prime will be IKA exponential to IKX minus IK B exponential to minus IKX. So when you substitute x equal to 0, it will become IKA minus IKB. And then for this one, phi 2 prime x will be IKB KBC exponential to IKBX. So when you substitute x equals to 0, it will become IKBC. So I can be cancelled. It becomes this one. So finally, we have these two equations, 1 and 2. And the refraction coefficient is like b over a, and then take the absolute value square. and it will become k minus kb over k plus kb, and then take the square. Because for this one, you will have a k. From this one, you will have k a minus b equals ckb. And actually, c is a plus b, which means c is k, a plus b. Sorry. C is a plus b, kb. So you can rearrange the term. We have ka, kb, a. So we have a, k minus kb. And then we can move this term to the right side, so we will have b, k plus kb. And then finally, we will have b over a to be k minus kb over k plus kb. So finally, R is nothing but this one. And then the transmission coefficient is like, so it feels like you have the incident, which is maybe you can call it 1 or whatever amount. So part of it is refracted, and this one is b over a absolute square, and then the remaining is can go through, which means this part is transmit. So r plus t should be equals to 1, because original the incident wave is 1, the incident electron is 1, and then part of it is reflect, and then the remaining can go through. So this is a 1 minus r, and 1 minus r is actually this one, because this is a k plus kb square and then minus k minus kb. So it should be like that, or it should be 4 k. This should be. Okay, so any question regarding to this one? No, let's have a break.